Let's take a look at the graph of the tangent function. The tangent function, you can think back to the unit circle. We can get its values by putting the second coordinate, the sine value, over the first coordinate, the cosine value. So I can write tangent as sine x over cosine x. That's a fraction. We know some things about how fractions work. Tangent x is going to be equal to 0 wherever its numerator is equal to 0. That's the sine. So tangent x is 0 when sine x is 0. And that happens when x is, let's see, sine of 0 is 0, sine of pi is 0, sine of 2 pi, 3 pi. We can go down the other way, negative pi, negative 2 pi, on like that. All those values, dot, dot, dot. We can say that succinctly. If I let n be any integer, the tangent function has a value of 0 at integer multiples of pi. So that's good. That gives us a bunch of points on the graph of the tangent function. In a fraction, when the denominator is 0 and the numerator isn't, we get a place where that fraction is undefined. So the tangent function is going to be undefined everywhere the cosine function is 0. So we'll think where that happens. That happens at, well, let's see, cosine pi over 2 is 0. Cosine 3 pi over 2 is 0. We know those two from the unit circle. And we can keep going coterminal angles with both of those. So in the negative direction, minus pi over 2, pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2, 153 pi over 2. Any odd number multiple of pi over 2, the cosine value is 0, so the tangent function is undefined. We can say that fancy also. These are, to say in English, odd number multiples of pi over 2. So there's the pi over 2 part. I just have to make an odd number here. If I let n be any integer, like we did up above there, could be even or odd. If I multiply it by 2, now it's even. Even numbers are multiples of 2. But I want odd number multiples of pi over 2. So I can get from an even number to an odd number by adding 1. Then there are all the places where the tangent function is undefined. What happens in a rational function where it's undefined? We get a vertical asymptote. So my tangent function is going to have vertical asymptotes at all of these values where the function is undefined. We have a pretty good start here. Let's get a graph going. So tangent of 0 is 0, tangent of pi is 0, tangent of 2 pi is 0, and then in between we're going to have these vertical asymptotes. There's 1 pi over 2, there's 3 pi over 2. If I go the other way, there's negative pi over 2. And now we're going to see what else is happening in between those asymptotes, because we don't quite have enough to make a graph yet. I do know the tangent of pi over 4 is 1, so there's a point. And I know the tangent of negative pi over 4 in quadrant 4 is negative 1, so there's a point. And we can think what happens. The sun is going in and out. It's making me nuts. We can think what happens with asymptotes. The closer we get to a vertical asymptote, we're going to shoot off next to it. We're not going to cross a vertical asymptote ever. Same thing this way. We end up with a graph that looks something like that. The period of the tangent function is not 2 pi, it's only pi. It repeats itself every pi. Let's see, named the vertical asymptotes already. The domain, well, I can put anything in there except for a place where the tangent function is undefined, which is where the asymptotes are. So I'm going to say all real numbers except where the asymptotes are. Did I just run off the edge of the world? Yes, I sure did. There we go. We'll move the world over. The range. Well, y values, I can hit any y value I want in there, top to bottom. So all real numbers for the range. And here, you get to look at me for a second, I think. If you ever wondered, this is it. Here's the nice Desmos version of y equals tangent x.